Okay, so today we're going to be looking at optimization. And optimization is the mathematical technique for finding a max or min of a function of several variables subject to constraint. And to introduce this, we're going to do a sample problem, and this is one of the main problems you're going to see a lot with optimization. A rectangular dog pound with 3 kennels, as shown in the figure, consists of a rectangular fenced area divided by 2 partitions. Determine the maximum possible area of this pound if 24 yards of chain link fencing is available for its construction. Okay, so the first thing you're always going to do is draw a picture. That's going to be your first step. Okay, so we've got our 3 kennels, and we're going to label them X and Y. You'll see why we do this later. Our next thing is going to write down all our knowns. So we know that we're going to be maximizing the area. That's what we do with optimization. We find maxes and mins. So we're going to be maximizing area. And we know that we have 24 feet of fencing. Our first equation for area is 3xy, 3x times y. And that's our optimization equation. But we also need a constraint equation that'll help us further simplify this equation later on. And so we do know that there's 24 feet of fencing, and we know this is equal to the 6x plus 4y. This is our constraint equation. And so our next step would be to solve for either x or y. And as we simplify, divide these all by 2. Subtract 3x from both sides, and divide by 2, and we get y equals 12 minus 3x over 2. Now the reason we solved for y here is so that we could put it back in to our original area equation, and now we only have things in terms of x instead of in terms of 2 variables. And so now that we put this back in to the area equation, we multiply in this 3x, and we get 36x minus 9x squared over 2. Which is equal to 1/2 36x minus 9x squared. Okay, so this is our simplified area equation in terms of x. The next thing we would do is take the derivative of this in order to further to get closer to our max and mins. So we take the derivative of this here. So this would be 36 and 18 to the 1/2. You move this over and you multiply all this by 1/2 and you get 18 minus 9x. Simplify this to x equals 2. And normally in an optimization problem you would make sure that this x value or y value here works with your domain. So if it was negative, if we got several negative zeros here, that would obviously not work in the domain because this is a real world situation. So this is positive, it's within the domain, we're good. Our next step would be to plug this x back in to our constraint equation and solve for y so that we can then solve for the maximum area. So we put in our 2 here and we find that y equals 3. Our final step would be plug in our x and y that we have found into our area equation and solve for our maximum area. So a equals 3xy, as we defined earlier, which is equal to 3 times 2, which is our x, and 3, which was our y. And we get that our maximum area is 18 square yards. So to sum this all up, with optimization, we're finding maxes and mins, maximizing something or minimizing something, whether like a distance or an area. And we do that by having an optimization equation and a constraint equation. And derivatives are involved, and we solve and find our max and min. So that is an example of optimization.